Hi, this is GEMath 1 Module 2 lecture, and the topic is the basic concepts of language of mathematics. So let me share with you this PowerPoint so that we could start discussing this subject, basic concepts of language of mathematics. So basic set theory. What is a set? George Cantor introduced the word set in 1879. The set is a collection of a well-defined and distinct objects called elements. The Greek letter epsilon is used to denote the membership of object in the set, and the brackets are used to enclose the elements of the set. The uppercase letters A, B, and C are usually used to name a set, and the lowercase letters A, B, C are sometimes used as the elements of the set. Example, the set A is a set of natural numbers less than 100. We have two ways of writing this down, the set builder form and the roster notation form. In set builder form, we could rewrite this statement into this statement in which A is equal to the set wherein X is an element of A such that X is a natural number where X is less than or equal to 100. In roster notation form, we write it as A is equal to the set containing 1, 2, 3, so on and so forth until 100. So the question is 3 an element of A? The answer is yes. 3 is an element of A. It is even mentioned in the roster notation form, and 3 is indeed less than or equal to 100, and 3 is a natural number. Now, is 50 an element of A? The answer is yes. 50 is an element of A because 50 is less than 100. But 101 is not an element of A because 101 is greater than 100. So now let's move forward. We have this set in a roster notation. N is equal to the set containing 1, 2, 3, so on and so forth. We also have this set, example of a set in roster notation. It meant that it is from negative infinity, until negative 3, 2, negative 1, 0, 1, 2, 3, so on and so forth until positive infinity. Also, we have this one in set builder notation. Q is equal to the set wherein X is an element of Q such that X is equal to P over Q, where Q, P, and Q is an element of Z, as mentioned before, and Q is not equal to 0. And lastly, R, in which X is an element of R such that X is either rational or irrational. These sets actually is the numbers or the number theory sets. The set of natural numbers, N, the set of integers, Z, the set of rational numbers, Q, and the set of real numbers, R. Using the set builder notation, given that R denotes the set of all real numbers, Z denotes the set of all integers, and Z minus denotes the set of all negative integers, then describe each of the following sets. A is equal to the set wherein X is an element of R, such that X is greater than negative 5 or less than 1. Or we could say wherein negative 5 is less than X and the X is less than 1. And we have also another example. B is equal to the set wherein X is an element of Z such that X is greater than negative 5 but less than 1. The question is, are these two the same? The answer is no, because Z is integers and R is real numbers. For instance, negative 3/2. Negative 3/2 actually is an element of A, but negative 3/2 is not an element of B because negative 3/2 is not an integer. How about C? C is a set wherein X is an element of Z minus, such that -5 is less than X and X is less than 1. So, as this statement says, we could read it as an element. We could read A as X is an element of a set of real numbers such that -5 is less than X and X is less than 1. So how about -3/2? Is -3/2 an element of Z? C. The answer is no. -3/2 is not or do not belong to the set of negative integers. How about 0? Is 0 a subset of A? Or rather 0 an element of A? Yes, 0 is an element of A. How about B? Is 0 an element of B? Yes, 0 is an element of B. How about C? 0 is not an element of C because the set of negative integers does not contain 0. Next, subset of a set. The set A is a subset of set B if A, denoted as subset of B, if and only if every element of A is in B. So, example, let M be a set containing these letters, G, R, E, A, T. Tell if the following sets is a subset of the set M. A, the set containing AT. Yes, this is a subset of A, or the subset of M rather, because A and T are all elements of M. How about B, the set containing EAT? Yes, this is a subset of M, because E, A, and T are all elements of M. How about T, the set containing TEAM? Is this a subset of M? The answer is no, because although T, E, and A are elements of M, M is not an element of M. Therefore, the set containing TEAM is not a subset of M. How about this one? The set containing RGETA. Is this a subset of M? The answer is yes. Remember, a set is always a subset of itself. So RGETA is a subset of M. Now, let's take another example. Proper subset of a set. A is a proper subset of A, denoted by A, a proper subset of B, if and only if every element of A is in B, but there is at least an element of B that is not in A. Example, let A be equal to 1, 4, and 3, or a set containing 1, 4, 3, and B be a set containing 1, 2, 3, 4, 5. Is A a proper subset of B, or denoted as A a proper subset of B? These two statements are the same. The answer is yes. A is a proper subset of B because every element of A is in B, but there are elements of B that is not in set A. For instance, the number 2 is in set B, but it does not appear in set A. 2 is an element of B, but not an element of A. Henceforth, A is a proper subset of B. So now let's take this example. Let A be equal to the set containing all the positive integers. And let's agree that the set containing all the positive integers does not contain 0. B is equal to the set in which n is an element of negative integers, that n is greater than or equal to 0, but less than or equal to 100. And B, or rather C, is equal to the set containing 100, 200, 300, 400, and 500. Now, tell if each of the following is true or false, and if false, explain why. Is B a subset of A? If you have agreed that the set containing positive integers does not contain 0, then B is not a subset of A because B contains 0. How about C? Is C a proper subset of A? We could agree that C is not a proper subset of A, or rather C is a proper subset of A because C, every element of C is present in A. For instance, 100, 200, 300, 400, and 500 is also an element of A. They are positive integers. But there are elements of A that is not an element of C. For example, 3. 3 is a positive integer, but 3 is not an element of C. How about this one? C and B have at least one element in common. That is true, 100. How about B? Is C a subset of B? The answer is no, because there are elements in C that is not present in B. And lastly, is C a subset of C? The answer is yes. You are always a subset of yourself. So C is always a subset of C. Now, subsets of sets. Let's S be a set containing the elements A, I, R. What are the subsets of S? First, the set containing nothing or empty. The set containing nothing is a subset of S because it has an element that is also present in S, nothing. So this is actually a subset of all set. The set containing nothing or null set is a subset of all sets. Now, the set containing R. Yes, the set containing R is subset of S. So is the set containing A, the set containing I, the set containing AI, the set containing IR, and the set containing AR. And most especially, the set containing IAR. Again, all the elements of the set containing IAR is present in set S. Now, the power set. The power set is a set whose elements are its subsets. So let S be equal to AIR, the set containing AIR, and let the power set of S is based on the following. Okay? So the power set of S is this one. Sorry for the delayed animation. So the power set of S is equal to the set containing nothing, empty, the set containing A, the set containing R, the set containing I, the set containing AI, the set containing AR, the set containing IR, and the set containing IRE. The set that contains those elements is the power set. So let us try to answer the following. A, an element of the power set of S. Is A an element of the power set of S? The answer is no. A is an element of S, but A is not an element of the power set of S. What is the element of the power set of S is the set containing A. Again, the set containing A is the element of the power set of S. As like this one. The set containing A is an element of the power set of S. Is this an element of S? No, because S does not contain a set that contains A. How about the set containing A? Is this a proper subset of the power set of S? The answer is yes, because as we have said, the proper subset is a set that contains an element of a set, and this set have at least one element that is not part of the element of this set. So the set containing A is an element of the power set. Henceforth, the set containing A is a subset of the power set of S. The set containing AR is a subset of the power set of S. The answer is no. The set containing AR is a proper subset of S, but it is not a proper subset of the power set of S. Rather, the set containing AR is an element of the power set of S. So the question is, how many elements does the power set of S have? So we've counted it. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So 8. So when we talk about how many number of elements, we meant the cardinality. What is the cardinality of the power set of S? It is said that the cardinality of the power set of S is equal to 2 raised to the cardinality of S. Meaning, the number of elements that the power set of S have is equal to 2 raised to the number of elements that the set of S have. To make it clearer, if it has no element, how many subsets does it have? It means what is the cardinality of its power set? So 2 to the 0 is 1. So if it has no element, then it has one subset. And what is that? The empty set. How about if it has one element? It has 2 subsets. If it has 2 elements, it has 4 subsets. If 3, 8. If 4, 16. How about x elements? It is equal to 2 raised to the x. So now let's check our progress. Given the set A, B, and C, tell whether each of the following is true or false. Is 2 an element of C? Let's reveal everything. Is 2 an element of C? The answer is yes. 2 is an element of C. How about the set containing 2? Is it an element of A? The set containing 2 is an element of A. You could see that one here. It's an element of A. You could see that. How about the set containing 2? Is it a subset of B? The answer is yes. The set containing an element of B is a subset of B, and the set containing 2 is an element of B. Henceforth, the set containing 2 is a subset of B. Is C a proper subset of A? The answer is yes. C is a proper subset of A. C contains an element that is also an element of A, and that is 2. Is A a subset of B? The answer is yes. Every element of A is present in B. How about B a subset of A? The answer is yes, because every element of B is present in A. Now we have another lesson learned. If A is a subset of B and B is a subset of A, then we can say that A and B are equal sets. Again, if A is a subset of B and B a subset of A, then we can say that A and B are equal sets. So let's talk about Cartesian products. Given set A and B, the Cartesian product of A and B is denoted as A cross B. So it is a set of all ordered pairs AB wherein A is in A and B is in B. Symbolically, A cross B is equal to the set containing the set of ordered pairs AB, such that A is an element of A and B an element of B. Example. Let A be equal to 1, 3, negative 4, and B equal to 0, 3. Find A cross B, B cross A, and B cross A. So the solution, A cross B is a set of ordered pairs in which the first element is present in A, so that's 1. And the second element is present in B, that's 0. Then 1, 3. 1, element of A, 3, element of B. Then 3, 0. 3, element of A, 0, element of B. Then 3, 3. 3, element of A, 3, element of B. Negative 4, 0. Negative 4, element of A, 0, element of B. And negative 4, 3. Negative 4, element of A, 3, element of B. So we could see here that as we continue on, we just distribute the value 1 to 0, 1 to 3, 3 to 0, 3 to 3, negative 4 to 0, negative 4 to 3. If we B cross A, then we get a different set. Now, is A cross B equal to B cross A? The answer is no, they are not equal. By doing so, because we now have ordered pairs, we could plot this in a coordinate plane, or what we call as Cartesian, plane Cartesian, or Cartesian plane rather. 1, 3 and 3, 1 are different. Remember that. 1, 3 and 3, 1 is not the same. So that is the end of our lecture for today. And hopefully we could clarify things when we meet up on synchronous meeting next week. So, goodbye and God bless.